Welcome to this explainer. Look, when you and I think of the Roman Empire, we're probably picturing gladiators, right? Or colossal aqueducts and those massive stone amphitheaters. We know them for their brute force infrastructure and their sprawling conquests. But hidden right behind all those marble columns and the military might was this quiet, almost secret world of incredibly advanced technology. The Romans were literally sitting on the edge of an industrial revolution, nearly 2 millennia before the actual one happened. Okay, let's dive into this. How in the world did a fully functional vending machine exist 1800 years ago? I mean, long before electricity, long before anything resembling the modern era. You could walk up to a seemingly ordinary clay jar, drop in a coin, and it would automatically dispense a perfectly measured portion of wine or holy water. No way, right? To understand how this was even possible, we really need to meet the genius behind the machine, a guy named Hero of Alexandria. Honestly, think of him as the ancient Tony Stark of the Roman Empire. He was this brilliant Greek engineer and inventor living in Alexandria while it was under Roman rule. And while Leonardo da Vinci gets all the historical glory today, Hero was out there designing machines that were centuries, sometimes millennia ahead of their time. So here's the agenda for our explainer today. We're going to cover 1, the ancient Tony Stark, 2, the first steam engine, 3, self-healing concrete, 4, the first mass production, and 5, miniaturization and precision. Let's see how close Rome actually came to an industrial age. Starting off with Section 1, the ancient Tony Stark and his engineering magic. Picture this for a second. A priest walks up to a grand Roman temple. He pauses before these massive, unbelievably heavy bronze doors, and he simply lights a small fire on an altar right next to the entrance. Without a single human touch, the colossal doors just slowly swing open. The crowds obviously thought it was absolute magic, but it wasn't magic. It was pure, brilliant engineering by Hero. Here's how he pulled it off. Hidden beneath that altar, water and air were sealed in a container. When the fire was lit, it heated the air, causing it to expand and built pressure. That pressure forced the water through a pipe into a second container. As this second container filled up, it got heavier and heavier. That sheer weight pulled down on ropes that were wrapped around poles, which mechanically pulled those heavy doors open. And the absolute best part, when the fire went out, the air cooled down, creating negative pressure that sucked the water right back, perfectly and automatically closing the doors behind the priest. The whole system just reset itself. Now, let's break down the mechanics of that ancient vending machine we talked about, because it's so elegant. Step 1, you drop your coin into the top of the jar and it lands on a small pan attached to a counterweight. Step 2, the weight of that coin tilts a lever, which pulls open a valve to start pouring the wine into your cup. Step 3, as the pan tilts further and further down, the coin eventually just slides right off into the bottom of the jar. The counterweight drops back down, snapping the valve shut. Boom! A perfectly measured pour, totally automated. This is a real game changer when you realize this incredible concept wouldn't be reinvented until a newspaper dispenser came along in 1822. Moving right along to Section 2, the first steam engine, which is honestly Rome's greatest missed opportunity. This is, without a doubt, history's biggest what-if moment. Hero didn't just stop at automating doors and drinks. He actually built a working steam engine in the 1st century. It was called the Iola pile, and it was the very first documented reaction steam turbine in human history. Basically, it used a fire beneath a sealed kettle to boil water. The steam rose up through pivoting tubes into a hollow metal sphere and shot out of 2 opposing nozzles on the sides, which forced the entire sphere to spin rapidly. I mean, it was a functioning engine. But then you compare that to 1712. The Romans just looked at this thing and saw a neat little toy, a party trick to entertain guests, rather than a machine capable of doing real work. They completely missed the fact that this exact core principle would be the very thing to reshape the modern world when it was finally reinvented for industrial labor centuries later. Okay, on to Section 3, self-healing Roman concrete and a massive 2023 breakthrough. Have you ever noticed how our modern concrete structures start to crumble and crack after just a few decades? Yet Roman structures are still holding strong nearly 2,000 years later. Well, in 2023, MIT researchers finally solved why. When scientists used to analyze Roman concrete, they kept seeing these little white chunks of lime and just assumed, the Romans were sloppy at mixing their materials. But it turns out, actually, scratch that. It wasn't sloppy at all. It was highly intentional. The Romans used a process called hot mixing. They deliberately mixed volcanic ash, quicklime, and water at extreme temperatures. This specific, super high heat chemical process left these reactive lime chunks scattered all throughout the concrete.
And this hot mixing created an absolutely incredible defense mechanism. When cracks naturally form in a regular building and moisture seeps in, modern concrete just degrades. But the Roman concrete actually reacted to the water. So, step 1, water enters the crack. Step 2, that water hits those little leftover chunks of lime, causing them to dissolve. Step 3, this triggers a chemical reaction that creates a calcium-saturated solution that flows right through the crack, essentially gluing the concrete back together. It's repairing itself. When MIT tested this, the damaged concrete completely healed itself in just 2 weeks. This self-healing ability is exactly what allowed Romans to build massive, unreinforced structures, like the Dome of the Pantheon, and run 400 kilometers of aqueducts across super rugged terrain without them collapsing.
Which brings us to Section 4. The first mass production, happening 1,500 years before the concept of a factory even existed. So, feeding the massive Roman Empire led to industrial-scale food production way before the word factory was ever a thing. Down in the south of France, archaeologists uncovered this colossal flour mill complex that featured an astonishing 16 immense water wheels. 16. They were all lined up sequentially down a steep hill, powered entirely by flowing water from 2 dedicated aqueducts. The wheels worked in a continuous chain of motion, one powering the next, to turn heavy millstones inside the buildings. This wasn't just some quaint village setup, this was heavy industry, and quite possibly the first real production line in human history. The sheer output of this facility was just staggering, 25 tons. Because of this highly automated setup, it only took an estimated 30 workers to run this entire massive production line, just 30 people. And they were churning out an astonishing 25 tons of flour every single day to be transported back to the city. To put that into perspective, that breaks down to nearly 1,000 kilos of flour per worker daily. So, with all these massive moving parts and complex logistics, you kind of have to wonder, how did they keep track of time before electricity? Because sundials were utterly useless on a cloudy day, right? Well, to answer that, we have to look at what happens when the Roman Empire needed to go really small and incredibly precise. Let's get into Section 5, miniaturization and precision, or really, their absolute mastery of scale. To track time, the Romans used automated water clocks designed by a Greek inventor named Cassibius. These things were powered purely by gravity and flow, and they mastered such granular precision that they even used a smart system of gears to adjust their time charts for the changing lengths of daytime across different seasons. The Romans completely mastered this kind of granular mechanical precision. And to prove just how precise they got, in 2023, a metal detectorist made a totally shocking discovery in a quiet field about 3 hours south of Hamburg, Germany. Buried underground for 1,600 years, he unearthed a fully intact Roman lock made entirely of gold. And this wasn't just some simple decorative trinket, it was a highly complex, highly functional mechanical device. Now, the scale here is going to give you whiplash. When you hear lock, you naturally picture something you can hold comfortably in the palm of your hand, right? But this golden lock was, quote, half the size of a Coca-Cola cap. Just let that sink in for a second. We're talking about literal microscopic mechanical engineering, built by hand well over a millennium and a half ago. And despite its microscopic size, this tiny artifact operates exactly like a modern padlock. You insert a tiny key, you turn it, and a complex internal mechanism smoothly releases a chain link. The whole shebang. All of this engineering was miniaturized, likely just to secure a small chest or a jewelry box. This extreme level of craftsmanship was achieved without any modern magnifying tools or precision machinery. In fact, to even properly study how the intricate internal mechanisms functioned, modern experts actually had to build a historically accurate replica 4 times larger than the original just to see what they were doing. So we've seen their self-healing concrete, their automated factory lines, their vending machines, and their microscopic golden mechanics. It really leaves us with this mind-bending final thought. If Rome had recognized the true power of their steam engine, if they had taken that oleopile from a fun party trick and turned it into a factory power source, where would humanity be today? The advanced tech of the Roman Empire proves they were standing right on the precipice of an industrial revolution, leaving us to wonder just how totally different our modern world would look if they had taken that final step. Thanks for joining me on this explainer.